Welcome! In this session, we'll explore problem number 1466, reorder routes to make all paths lead to the city 0. This intriguing problem challenges us to reorder road directions to ensure all roads lead to city 0. Let's dive in and uncover the solution together. In this problem, we are tasked with reordering roads in a network of cities to ensure that all paths lead to city 0. The cities are numbered from 0 to N1, and the roads are given as a list of directed connections. For each road represented as A, B, the direction is from city A to city B. Importantly, the roads are directed, meaning you can only travel in the specified direction. The goal is to determine the minimum number of roads we need to reverse to make it possible to travel from any city to city 0. Additionally, we are allowed to reverse the direction of any road, but only once per road. The output will be an integer representing the minimum number of reversals needed to achieve this configuration. Let's look at an example to understand the problem better. Here, we have n equal to 6 and a list of roads represented as connections. Initially, the roads are directed as follows: 0 to 1, 1 to 3, 2 to 3, 4 to 0, and 4 to 5. To ensure that all paths lead to city 0, we need to reverse some roads. Specifically, the roads 1 to 3, 2 to 3, and 4 to 5 must be reversed. After these changes, all cities are connected to city 0, and the total number of roads reversed is 3. This example demonstrates how we identify the roads that need to be reordered to achieve the desired configuration. Here's another example with n equal to 5. The initial connections represent roads directed as follows: 1 to 0, 1 to 2, 3 to 2, and 3 to 4. To ensure all paths lead to city 0, we need to reverse the roads 1 to 2 and 3 to 4. After these reversals, every city is connected to city 0. The total number of roads that need to be reordered in this case is 2. This example highlights the importance of carefully analyzing the road directions and determining the minimum changes necessary to achieve the objective. In this final example, we have n equal to 3, with roads directed as 1 to 0 and 2 to 0. Here, all paths already lead to city 0. Since no roads need to be reversed, the output is 0. This scenario demonstrates that when the roads are already configured correctly, no changes are needed, and the solution is simply 0. This is the ideal case where the network requires no adjustments to meet the problem's requirements. Now, let's discuss some edge cases. First, consider the smallest possible input, where n equals 2, and there is only one road directed from city 1 to city 0. In this case, no roads need to be reversed. Next, imagine all roads are already pointing toward city 0, such as connections like 1, 0, 2, 0, and 3, 0. Again, no changes are needed, and the output is 0. Finally, consider the opposite scenario where all roads point away from city 0, such as connections like 0, 1, 1, 2, and 2, 3. Here, every road must be reversed to ensure all paths lead to city 0. These edge cases help us understand the range of possible inputs and how the solution adapts to different configurations. When tackling this problem, we first considered several approaches to understand the best way to reorder the roads. One straightforward idea is the brute force approach. Here, the intuition is to just iterate through all the connections repeatedly, checking the direction of each road and reordering it if necessary. While this is simple to conceptualize, the implementation involves traversing the list of connections multiple times to realign the roads, fixing one misdirected road per traversal. This leads to a time complexity of n squared, making it highly inefficient for larger graphs. Importantly, it misses the opportunity to leverage the tree structure of the problem, where we know there are n cities and n1 edges. Another approach is to use DFS or BFS with an adjacency list, which treats the roads as a graph. In this strategy, each city is a node, and we represent both incoming and outgoing roads in an adjacency list. For instance, an outgoing road might be marked as B, true, and an incoming road as false. By performing a DFS or BFS traversal starting from city 0, we can explore all nodes and count how many outgoing roads need to be reversed. This approach is significantly more efficient, with a time complexity of n, and it directly utilizes the tree structure of the problem. As a result, it avoids the inefficiencies of the brute force method and aligns well with the problem constraints. Another method we considered is the union find algorithm, which uses a disjoint set structure to group cities into components. The idea here is to ensure that all roads ultimately lead to the same parent, which is City 0. As we build the union-find structure, we can track misaligned roads that need to be corrected. While this approach has a nearly linear time complexity of O n asterisk alpha n, where alpha n is the inverse Ackermann function, it is more complex to implement compared to the DFS or BFS method. Furthermore, the union-find algorithm does not align as naturally with the problem's tree structure and constraints as the DFS/BFS approach does. Given these considerations, we chose the DFS or BFS approach with an adjacency list as our strategy. This decision was based on several key observations. First, the problem is fundamentally a tree traversal problem, given that the graph is connected in acyclic with n cities and n1 roads. Second, our main task is to count outgoing roads that need to be flipped, and this aligns perfectly with DFS or BFS. Finally, representing the roads as bidirectional edges in an adjacency list allows us to traverse the entire graph starting from City 0 without worrying about direction constraints up front. We simply increment our counter when we encounter an outgoing edge that requires reversal. This approach is both efficient, with a time complexity of O n, and straightforward to implement, making it a natural fit for the problem at hand. When comparing the different approaches, we see clear trade-offs. The brute force method is highly inefficient, with an O n squared complexity, making it unsuitable for larger graphs. On the other hand, while the union-find algorithm is efficient and has a near-linear time complexity, it is more complex to implement and doesn't align as intuitively with the tree structure of this problem. The simplicity and clarity of the DFS/BFS approach make it stand out. It is easier to implement, highly intuitive for a tree structure, and directly addresses the problem's requirements by efficiently counting outgoing roads that need to be flipped. In conclusion, the DFS/BFS approach strikes the perfect balance between simplicity, efficiency, and clarity. It leverages the problem's tree structure effectively, operates within optimal time and space complexity, and avoids unnecessary complications. For these reasons, it is the best choice for solving this problem. In this problem, we are tasked with ensuring that all roads in a network of one-way roads lead to the destination city, which is City 0. Some roads are misdirected, meaning they don't follow the required direction, and our goal is to determine the minimum number of roads that need to be reordered to fix this. The first step in solving this problem is to represent the road network as a directed graph. We use an adjacency list for this purpose. For every connection between two cities, such as U, V, we add V plus 1 to the adjacency list of U, indicating a road from U to V. Similarly, we add U minus 1 to the adjacency list of V, representing a reverse road from V to U. This dual representation of forward and reverse roads is crucial because it allows us to easily identify which roads are misdirected and need to be reordered. By structuring the graph this way, we have a clear framework for analyzing the road directions as we proceed to solve the problem. Now that we have the graph representation, the next step is to traverse the graph using breadth-first search, or BFS. BFS is ideal for this problem because it allows us to explore all nodes layer by layer, starting from the destination city, which is City 0. To implement BFS, we initialize a queue with City 0 as the starting point. We also maintain a visited set to keep track of which nodes have already been processed, avoiding redundant computations. Additionally, we introduce a variable reorder_count to track the number of roads that need to be reordered. As we process each node, we dequeue it from the queue and examine its neighbors from the adjacency list. For each neighbor direction, if the neighbor has not been visited, we mark it as visited and check the direction of the road. If the direction is +1, indicating a misdirected road, we increment reorder_count. The neighbor is then enqueued for further exploration. This systematic approach ensures that we account for all roads and only reorder those that are misdirected, all while avoiding redundant checks. After traversing all nodes in the graph, the final step is to return the value of reorder_count, which represents the minimum number of roads that need to be reordered to ensure all paths lead to City 0. This result is obtained after processing every node and verifying the direction of all connected roads. The key insights behind this approach are worth emphasizing. First, the graph representation, which includes both forward and reverse directions, is essential for efficiently identifying misdirected roads. Second, BFS is particularly effective here because it ensures that all nodes are visited in the correct order, minimizing redundant checks. Finally, starting the traversal from the destination city simplifies the problem, as it allows us to directly determine the required direction of each road relative to City 0. These insights demonstrate why the algorithm is both efficient and well-suited to the problem. To implement this algorithm, we rely on three key data structures. The adjacency list is used to store the road network in a way that allows constant time access to neighbors. This is crucial for efficiently exploring the graph. The queue is the backbone of our BFS traversal, ensuring that nodes are processed in the correct order. The visited set is equally important, as it tracks the nodes we have already processed, preventing redundant work and ensuring that each node is handled only once. From a complexity perspective, the algorithm is highly efficient. The time complexity is O(n), where n is the number of nodes, because BFS processes each node and its edges exactly once. The space complexity is also O(n), as we need space for the adjacency list, the queue, and the visited set. These factors make the algorithm both space efficient and time efficient, enabling it to handle large road networks effectively. This solution addresses the problem of reordering routes to ensure all paths lead to City 0. The approach uses breadth-first search, BFS, to traverse the graph and count the minimum edges to be reversed. First, the graph is represented as an adjacency list where each edge is annotated with a direction. The connections list is processed to populate the graph. For every u(v) in connections, both the original edge, u-v, with a direction of 1 and the reverse edge, v-u, with a direction of 0 are added to the graph. This allows us to track whether an edge in the original graph requires reordering. The BFS starts from City 0, using a queue to manage the traversal, and a visited set to prevent revisiting nodes. For each city dequeued, its neighbors are processed. If a neighbor has not been visited, the edge's direction is checked. If the direction is 1, it indicates a road requiring reordering, and the reorder underscore count is increment. The neighbor is then enqueued for further traversal. The algorithm continues until all reachable nodes have been processed. The result is the total number of roads that need to be reordered, as determined by the reorder underscore count variable. This approach is efficient, with a time complexity of O(n), where n is the number of cities, since every node and edge is processed exactly once. The space complexity is O(n) for the graph representation and BFS data structures. Here, we start by defining our solution class and the method minReorder, which accepts the number of cities, n, and a 2D array of connections representing the directed roads between cities. To efficiently work with the graph, we create an adjacency list using a hash map. Each city is mapped to a list of its neighbors, where each neighbor is stored as an array containing the neighboring city and a flag indicating whether the edge is in its original direction. A value of 1 indicates the original direction, while 0 represents the reverse direction. Next, we iterate through the connections array to populate the adjacency list. For each connection, u(v), we add an edge from u to v with a flag of 1, and from v to u with a flag of 0. This ensures we can traverse both directions when processing the graph. We then initialize a breadth-first search, BFS, starting from City 0. A queue is used to explore connected cities, and a visited set keeps track of cities already processed. Finally, we introduce a variable reorder count to keep track of the number of edges that need to be reversed as we traverse the graph. Now, during the BFS loop, we process the current city by removing it from the queue and marking it as visited. For each neighboring city, represented as neighbor, we extract the next city and the direction of the edge. If the neighboring city has not been visited yet, we check the direction. If the edge points away from City 0, indicated by a direction value of 1, we increment reorder count because this edge will need to be reversed to make it point toward City 0. Regardless of the direction, we add the next city to the queue for further exploration. Once the BFS completes, we have traversed all cities and counted the necessary edge reversals. Finally, the method returns reorder count, which represents the minimum number of edges that need to be reordered to ensure all paths lead to City 0. Here, we start with a basic test case where there are 6 cities and the given connections between them are represented as directed edges. The first step is to construct a graph using an adjacency list. Each connection is stored twice, once in its original direction, marked with a value of 1, and once in the reverse direction, marked with a value of 0. This allows us to differentiate between edges that need reordering and those that don't. After processing all the connections, the adjacency list for the graph is displayed. For example, City 0 has outgoing edges to City 1 in the original direction and to City 4 in the reverse direction. Similarly, City 4 has an incoming edge from City 0 and an outgoing edge to City 5. This graph structure will be used in the next steps to determine the minimum number of edges that need to be reordered to ensure all paths lead to City 0. Now, we perform a breadth-first search starting from City 0. We initialize a queue with City 0, an empty set to keep track of visited cities, and a counter, reorder_count, to count the number of edges that need to be reordered. First, we process City 0 by marking it as visited and checking its neighbors. The edge to City 1 is in the original direction, so we add City 1 to the queue and increment reorder_count to 1. The edge to City 4 is in the reverse direction, so we simply add City 4 to the queue without incrementing reorder_count. Next, we process City 1. We skip City 0 as it's already visited and then add City 3 to the queue because the edge to City 3 is in the original direction, which means we increment reorder_count to 2. Finally, we process City 4. We skip City 0 again and add City 5 to the queue because the edge to City 5 is in the original direction, incrementing reorder_count to 3. After processing City 4, the updated state of the queue includes Cities 3 and 5, and the visited set contains Cities 0, 1, and 4. Now, we process the remaining cities in the queue. City 3 is marked as visited, and its neighbors are checked. Both City 1 and City 2 are already visited or do not require reordering, so no further reordering is needed. Similarly, processing City 5 reveals that its neighbor, City 4, is already visited, meaning no additional changes are required. At this point, all cities have been visited, and the BFS traversal is complete. The final reorder_count is 3, indicating that 3 edges need to be reordered for all paths to lead to City 0. Moving on to the second example, we have a smaller and simpler graph where all connections are already in the correct direction. For the second example, we again start by constructing the graph using an adjacency list. Here, City 0 has outgoing edges to both City 1 and City 2, with both edges in the original direction, marked as 1. Cities 1 and 2 each have reverse edges back to City 0, marked as 0. Once the graph is built, we perform a BFS traversal starting from City 0. The queue is initialized with City 0, and reorder_count begins at 0. When processing City 0, both neighbors, City 1 and City 2, are added to the queue, and reorder_count is incremented by 2 because both edges are in the original direction. Next, we process Cities 1 and 2. Since their only edges are reverse edges back to City 0, no further reordering is needed. The BFS traversal ends with reorder_count equal to 2, which is the final output for this example. Let's now examine a third example where the graph represents a single path. In this third example, we have 4 cities, and the connections form a star topology with all paths leading directly to City 0. The graph is constructed as an adjacency list where City 0 has incoming edges from Cities 1, 2, and 3, all marked as reverse edges with a value of 0. Cities 1, 2, and 3 each have outgoing edges to City 0 in the original direction, marked as 1. Once the graph is built, we can clearly see that every path already leads to City 0. This structure will result in no edges needing reordering during the BFS traversal. Performing the BFS traversal for this example, we start from City 0 with an empty visited set and reorder_count initialized to 0. City 0's neighbors, Cities 1, 2, and 3, are added to the queue. Since all the edges are in the reverse direction, no reordering is required. As we process Cities 1, 2, and 3, we find that their only neighbor, City 0, is already visited, so no further action is necessary. The BFS traversal completes with reorder_count remaining at 0. This confirms that no changes are needed for all paths to lead to City 0. The final output is reorder_count equal to 0, concluding this example. To analyze the time complexity of our solution, we start with the graph construction. The graph is represented as an adjacency list, where for each edge in the input, we perform 2 append operations, one for the original direction and one for the reverse. Since there are n cities, the number of edges is n1 in a connected tree. This means constructing the graph takes n time. Next, for the BFS traversal, each node is processed exactly once, and its neighbors are explored. Given that the total number of edges is also n1, the total number of neighbor visits is proportional to the number of edges. Therefore, BFS traversal also takes n time. Combining these steps, the overall time complexity of our solution is n. Now, let's examine the space complexity. For the graph representation, the adjacency list stores each node and its neighbors. Since there are n1 edges, and each edge is represented twice, once for each direction, the space required for the adjacency list is n. Additionally, the visited set keeps track of all visited nodes. In the worst case, all n nodes are visited, which requires n space. Finally, the queue used for BFS can hold up to n nodes in the worst case when all nodes are added to the queue. Summing these up, the total space complexity of our solution is n plus n, which simplifies to n. Let's compare this optimized solution to a brute force approach. A naive method would recursively traverse the graph, checking every edge to determine whether it needs reversing. However, this would lead to redundant checks and revisiting nodes, resulting in a time complexity of n squared for a connected graph with n nodes. Additionally, the recursive calls would increase space usage due to deep call stacks. In contrast, our optimized solution avoids redundant checks by using BFS and a visited set, ensuring each node and edge is processed exactly once. This reduces the time complexity to n and the space complexity to n. Whether in the best case, where the tree is already correctly oriented, or the worst case, where all edges need reordering, the algorithm consistently processes all nodes and edges once, maintaining a time complexity of n. The mathematical reasoning behind this solution lies in its efficiency. BFS ensures that each node and edge is visited exactly once, guaranteeing linear time complexity. The adjacency list allows for efficient edge lookups, while the visited set prevents redundant processing. Since both the time and space complexities scale linearly with the number of nodes, the solution is well suited for this problem. This linear scaling ensures optimal performance, even for larger graphs, making the algorithm both time and space efficient. Here are some common mistakes to watch out for when solving this problem. First, a frequent error involves incorrectly handling bidirectional roads. If you assume all roads are unidirectional and fail to account for their bidirectional nature, you might miss necessary reorders or misunderstand the graph structure. The fix is to treat the connections as bidirectional while explicitly tracking the directionality of each road. Another issue is inefficient traversal, which can lead to time limit exceeded errors. For example, using an n squared approach, like repeatedly checking all connections, won't work for large graphs where n can go up to 100,000. Instead, you should optimize your traversal using BFS or DFS, which ensures an n complexity. Lastly, not marking visited nodes is another common pitfall. Without tracking which nodes you've already processed, you risk infinite loops or redundant operations. To prevent this, always use a visited array or set, ensuring each node is handled only once during traversal. Additionally, improper initialization of the graph structure can lead to logical errors. For instance, if you don't clearly distinguish between directed and undirected edges, your implementation may misinterpret the need for road reordering. The solution here is to represent the graph using an adjacency list with clear direction indicators. Another mistake is misinterpreting the problem statement itself. Some may confuse this task with finding the shortest path or constructing a minimum spanning tree, which leads to implementing incorrect algorithms. To avoid this, carefully read and understand the problem requirements, focusing on the specific objective of reordering roads to make all paths lead to City 0. From an interview perspective, this problem offers valuable insights. It aligns closely with classic graph traversal problems, so recognizing that BFS or DFS is typically required can help you save time. Road networks often involve bidirectional graphs, so being clear about edge directionality is essential for solving these types of questions. Interviewers also like to test your awareness of edge cases, such as scenarios with no roads, all roads already correctly oriented, or a graph with a single node. When choosing between BFS and DFS, consider the trade-offs. BFS is often preferred for its iterative clarity, while DFS might be simpler to implement recursively. Finally, strong communication is key in interviews. Be explicit about your choice of data structures, such as an adjacency list, and explain why your chosen traversal method fits the problem. This problem is closely related to several other LeetCode challenges. For instance, Find the Town Judge and Keys and Rooms also involve graph-based reasoning, while Number of Islands focuses on connected components. Exploring these problems can deepen your understanding of graph traversal techniques. Regarding alternative approaches, DFS is a popular choice for this problem because it allows you to recursively traverse the graph and count misdirected roads. However, it comes with the risk of stack overflow in graphs with deep recursion. BFS, on the other hand, offers an iterative solution, avoiding recursion depth issues, though it requires managing a queue explicitly. Both methods are valid and should be chosen based on your comfort level and the constraints of the problem. Other potential approaches include union find and greedy algorithms. Using a union find, or disjoint set union, can help identify connected components and determine necessary road reorders. However, this method can be less intuitive for this specific problem and may require additional complexity for tracking road directions. Greedy algorithms might attempt to reorder roads based on local conditions, but they often fail to account for the global requirements of the problem, leading to suboptimal solutions. These approaches are worth exploring, but they come with trade-offs that might make them less ideal compared to BFS or DFS for this particular challenge. Great work! We've summarized key points for problem number 1466. Always remember to analyze the problem, consider edge cases, and optimize your approach. Thanks for joining, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!